Hey guys, good morning. I'm going to pick up here in chapter 11. I think this is part 4, although I'm somewhat losing my mind a little bit. So we covered ionic bonding in the last part, and I just want to give a general overlay of some other types of bonding in molecules. And again, this is a cursory view. Each of these is obviously a very intricate and detailed area, and so again, this is just an overview. So anyway, I want to take a look at some covalent bonding. And unlike in ionic bonds, where there's a transfer of an electron, here we have a sharing of electrons. And I guess the paradigmatic molecules here are going to be, as we move through this, are going to be either homonuclear diatomics, things like O2, F2, or heteronuclear diatomics, things like CO, HCl, and again, gas phase will be the primary phase that we will study these. And again, there's not much in your book to describe these. Again, the bonding in these can be complex, and if you get to polyatomic molecules, then this is complex quantum chemistry. But anyway, I want to highlight the energies of these bonds. So the energies are on the order of 200 to 500 kilojoules per mole. That actually translates to an energy of 2 to 5 electron volts per bond. Okay, so there's a nice conversion factor here that's probably worth remembering. So if you wanted to go from kilojoules per mole to EV per bond, you just want to multiply by 0.01. And so you can see that here already, right? So 200 to 500 kilojoules per mole, 2 to 5 EV per bond. So that's a nice conversion factor to have lurking around in the back of your mind. So again, we might touch a little bit on covalent bonding a little bit later when I talk about some more complicated bonding in this chapter. But for now, I just want to move on to the overall landscape here. So we have in general the category of what is called van der Waals. Let me erase all this. Van der Waals bonding, and again, a very complex array of bonds. but really important. And so these can be broken up into several subcategories. So one can think of van der Waals bonding as as um, as the overall category for the following subgroups. So first would be dipole interactions. Okay, these are for molecules that have a asymmetric distribution of electrons. For instance, HCl. HCl, for instance, and this is the Lewis diagram, Lewis structure for HCl. And again, for those of you who remember some chemistry, then you might remember that. It's to get an octet, or 8 electrons around each atom, hydrogen being one of the exceptions. But the bottom line is that chlorine, by virtue of it liking electrons, that is, it has a high electronegativity. Electronegativity is a measure of how much an atom likes to have electrons, and so one can think of hydrogen chloride. Again, this is gas phase. Okay, so this would be gas phase. Again, this is why this is complicated. We know that if this were in solution, then this would be called hydrochloric acid, and both the hydrogen and the chlorine would dissociate 100% into the hydrogen ion or hydronium ion and the chloride ion. But in the gas phase, hydrogen would be partially positive, the chlorine would be partially negative. In chemistry notation, this would be a dipole moment. A dipole moment in this direction. One puts the positive side on that tail to designate the positive side of the dipole moment vector. In physics, the dipole moment vector is actually in the opposite direction, but that's a topic for electricity and magnetism, which all of you will take at some later time. So one can have dipole interactions. They're not necessarily, they're not bonding interactions, but they are electrostatic interactions between, in this case, would be gas phase molecules of hydrogen chloride. You can have dipole induced dipole interactions. And so that would be the interaction between a molecule that has a dipole moment with a molecule that does not, and the dipole moment actually induces a charge redistribution in the neutral molecule, and consequently there's an interaction there. So dipole induced dipole. And then lastly, there's what are called dispersion forces. Sometimes called London dispersion. London dispersion forces. And in this particular case, we're talking about two atoms or molecules, right? That have no permanent dipole moment. And I should go back here actually, and so You guys may recall, I think we might have talked about this before, but if not, the dipole moment mu is equal to the charge, the magnitude of the charge on each atom here, times the distance of separation between the two. Okay, so that's the dipole moment, and so the dipole moment in general is equal to Q times D, where this is the charge on one atom. This is the separation between Q positive and Q negative in the molecule. And so you'll know the units, SI units, are going to be in units of Coulomb meters. But the unit that still is used actually quite frequently is the unit of the debye, named after Peter Debye, who was a Dutch physical chemist. And so the debye, 1 debye, capital D, is equal to 3.33 times 10 to the negative 30 Coulomb meters. Again, that's a nice unit to again have stored in the back of your mind. It's easy to remember because it's all threes, right? So 1 debye is 3.33 times 10 to the negative 30 Coulomb meters. So, but back to London dispersion forces. So these come about through the actual dynamic fluctuation of electron distribution around nonpolar atoms or molecules, and so things like things like H2, which is a homonuclear diatomic, right? Has no dipole moment. But the electron distribution around H2 does fluctuate in time, and these transient dipole moments will induce transient dipole moments in other H2 molecules around them, and these dispersion forces are attractive in nature. So it's important to know that these dispersion forces are attractive in nature, and responsible actually for things like H2 and O2 and helium, for instance, responsible for them being able to be liquefied, okay, because the liquefaction of those atoms and molecules then require an attractive interaction between them to be able to go from the gas state to the liquid state. So, so these London dispersion forces are what's responsible for that. Energies for these, again, for all of these above, the energies are small. They're on the order of 0.4 to 4 electron volts. Again, we can see now that they're approximately 100 times smaller than the covalent bonds or ionic bonds of species. So these energies are on the small side. And the last kind of interaction I want to talk about are what are called hydrogen bonds. And these typically are bonds that involve molecules that have high electronegativity atoms associated with them. So the classic examples of hydrogen bonding would be in water or in hydrogen fluoride. And so in water, for instance, water which has a structure which looks like so. Again, this would be the Lewis structure for water. And so, water molecules that are in the liquid state, oxygen is actually fairly electronegative, and so one would have what's called a hydrogen bond between, crapola, would have, what am I doing here? Let me get back to my sepia color. So here's 3 water molecules, and what would happen here is, these would be hydrogen bonds. These would be hydrogen bonds. And hydrogen bonding in water is actually the reason why water has such peculiar properties, right? And again, if it weren't for the hydrogen bonding in water, life would not exist on this planet, nor would it have evolved. And we can talk about that at some other time, but the fact that water exhibits hydrogen bonding, exhibits some very interesting physical properties. Its boiling point, its freezing point are all governed by the hydrogen bonding network in water. It's due to these physical properties that water exists as it does, and that life was able to evolve on Earth. The energies here, and HF has the same kind of hydrogen bonding between the highly electronegative fluorine and the hydrogen of other hydrogen fluoride molecules. The energies here, although small, are very significant, and they're on the order of 0.1 electron volt per bond. I should point out that it's hydrogen bonding. That keeps DNA in its what is called its duplex structure, its duplex helical structure, and again, during replication of a cell, that hydrogen bonding is unzipped, so to speak, so that each strand of DNA can go to each new cell and replicate itself. So hydrogen bonding is really super important in the solvent of life, water, and in the maintaining the information transfer as far as DNA is concerned. So hydrogen bonding really important. So anyway, I'm going to end right there, and then pick it up on molecular rotation and vibration in the next segment. All right, very good. Thanks.